A neutron star is what remains when a massive star dies. When the iron core of a giant collapses in a supernova, it does not halt at white dwarf density, but is crushed onward until it reaches the density of an atomic nucleus itself, and there, abruptly, it holds. The result is the most extreme stable object in the universe short of a black hole, roughly 1.5 times the mass of the Sun packed into a sphere only a dozen kilometers across, the size of a city. Its density matches that inside an atomic nucleus, so that a single teaspoon of its material would weigh about 1 billion tons. Its surface gravity is some 200 billion times that of the Earth, and light climbing away from it is stretched to radar wavelengths by 1/5 or more. Here, general relativity is not a small correction, but a leading-order effect, and the ordinary rules of matter are pushed utterly beyond anything we can reproduce. The birth of such an object is violent beyond imagining. In a star of more than about 8 solar masses, the core builds up iron from which no more energy can be squeezed, and once that inert core exceeds a critical mass, it collapses in less than a second, falling inward at 1/4 of the speed of light. The infall is halted only when the matter reaches nuclear density, and the strong nuclear force, together with the quantum pressure of the packed neutrons, abruptly stiffens and pushes back. The core rebounds, and that rebound, aided by a colossal flood of neutrinos, blows the overlying layers of the star out into space as the visible supernova. What is left behind at the center, hidden within the expanding wreckage, is the newborn neutron star, a ball of nuclear matter, forged in a fraction of a second, that will now cool and spin for billions of years. Inside, the star is layered like nothing else in nature. Beneath a thin atmosphere lies a solid crust of ionized nuclei, and as one descends, the nuclei grow ever more swollen with neutrons until, at a certain depth, neutrons begin to drip out of them and form a free superfluid sea. Deeper still, the nuclei may be squeezed into strange extended shapes that physicists nickname nuclear pasta, before dissolving entirely into the core, a uniform liquid of neutrons, laced with a few % of protons and electrons in perfect balance, and at the very center, where the density may climb to 10 times that of an ordinary nucleus, no one knows for certain what exists. It may be ordinary neutrons, or it may be something more exotic, a soup of hyperons, or a condensate of subnuclear particles, or even free quarks, liberated from the protons and neutrons that normally imprison them. The composition of that innermost core is one of the great open questions of physics. The name neutron star is itself a little misleading, and older than any evidence for the objects. They are not pure neutrons but a neutron-dominated mixture in careful balance, and they were conjectured on paper long before they were seen. In 1934, only 2 years after the neutron was discovered, Walter Baade and Fritz Zwicky proposed that a star could collapse into a body made of neutrons, and that the energy released would power a supernova. 5 years later, Robert Oppenheimer and George Volkoff performed the first calculation of such a star's structure, but for 3 decades the neutron star remained a theorist's curiosity, an object so small and faint that no one expected ever to detect one directly. The proof, when it came, would arrive from an entirely unexpected direction, as a ticking in a radio receiver. Before that story, consider what holds these objects up, for it is a close cousin of the physics of white dwarfs. A neutron star is supported at first approximation by degeneracy pressure, but now it is the neutrons that are degenerate rather than the electrons. Neutrons, like electrons, are fermions bound by the Pauli exclusion principle, so packing them together forces them into ever higher states of motion and generates a pressure that persists even at absolute zero. The reason the neutrons take over is itself revealing. As a white dwarf is compressed toward the Chandrasekhar limit, it becomes energetically favorable for its electrons to be captured onto protons, turning them into neutrons and neutrinos. The supporting electrons vanish, the star cannot stop at white dwarf density, and it collapses until the neutrons themselves and the stiff repulsion of the nuclear force provide a wholly new source of support at nuclear density. But describing the star's structure demands more than degeneracy, because gravity here is so strong that Newton's equations fail. In Newtonian physics, only mass gravitates. In Einstein's, energy and pressure gravitate too. The correct description is the Tolman-Oppenheimer-Volkoff equation, derived from general relativity for a static, spherical star, and every one of its relativistic corrections makes gravity stronger than the Newtonian estimate. The pressure that holds the star up itself adds to the weight it must support, and the curvature of spacetime steepens the pull toward the surface. The profound consequence is that no material, however stiff, can hold up an unlimited mass. For every possible kind of matter there is a maximum mass, a Tolman-Oppenheimer-Volkoff limit, beyond which nothing can prevent collapse into a black hole. Exactly where that limit lies depends on the equation of state, the relationship between pressure and density in matter above nuclear density, and this is the central unsolved problem of the field. Such densities cannot be reached in any laboratory, and the theory of the strong force cannot yet be solved from first principles in this regime, so physicists build the equation of state from nuclear theory at lower densities and extrapolate upward. A stiffer equation of state with higher pressure resists gravity better and supports a heavier star. Tellingly, Oppenheimer and Volkoff's original calculation, using a gas of non-interacting neutrons, gave a maximum mass of only about 7/10 of the Sun's, far below reality. This was not an error but a lesson. A free neutron gas is far too soft, and the repulsive nuclear force between particles, which they had left out, supplies most of the pressure in a real neutron star. Modern calculations give a maximum around 2 to 2 1/3 solar masses. That range is now pinned down by observation, and one of the most elegant methods relies on Einstein's theory itself. In a binary where a pulsar passes nearly behind its companion, the pulses that graze the companion are delayed by the warping of spacetime around it, an effect called the Shapiro delay. Timing that delay yields the masses of both stars directly, with no assumptions about the matter inside. One pulsar weighed this way tips the scale at about 2.1 solar masses, and another at perhaps 2.3, each setting a hard floor beneath the maximum mass. For any theory of dense matter that cannot support the heaviest observed star is simply wrong. From the other side, the gravitational waves of a neutron star merger constrain the maximum from above, bracketing the true limit near 2 solar masses. The radius supplies the complementary clue, and here a small X-ray telescope on the International Space Station has led the way. NASA-NICER instrument measures a neutron star's size by watching the X-rays from its hot magnetic poles flicker as it rotates, for the star's own gravity bends that light in a way that depends precisely on its mass and radius. The measurements place a typical neutron star's radius near 12 kilometers and, strikingly, show that even the heaviest neutron stars are not much larger than lighter ones. That fact alone rules out the very stiffest equations of state and points toward matter of moderate stiffness. Between the heavy masses, the NICER radii, and the gravitational waves, the walls are closing in on the behavior of the densest matter in the cosmos, even as its innermost composition stays hidden. The observational reality of neutron stars arrived through one of the iconic discoveries of 20th century astronomy. In 1967, Jocelyn Bell, a graduate student at Cambridge, working under Antony Hewish, was studying a newly built radio array when she noticed a faint, recurring smudge in the reams of chart recorder paper, a bit of what she called scruff. When she examined it closely, it resolved into a train of pulses of astonishing regularity, arriving every 1.337 seconds, as steady as a clock. Nothing known in astronomy pulsed so precisely, and the discovery would overturn the picture of what a dying star could become. The regularity was itself the puzzle. So precise and artificial did the signal seem that the team, half in jest, labelled it LGM1, for little green men, unable at first to rule out an intelligent origin. The hypothesis collapsed when Bell found a second source, then a third and a fourth, in different parts of the sky with different periods, for it was absurd that several separate civilizations would all be signalling Cambridge at once. And when the pulses were found to keep sidereal time, tracking the stars rather than the sun, they were fixed firmly to the celestial sphere. The first source was catalogued as CP 1919, and the discovery was announced in early 1968. A wholly new kind of object had entered astronomy. The explanation followed within months, and it vindicated a 30-year-old prophecy. The clock had to be small because nothing can pulse faster than light can cross it, and it had to be phenomenally stable. Thomas Gold and independently, Franco Passini proposed the answer, a rapidly rotating, strongly magnetized neutron star. The rotation is the clock, and a magnetic beam tilted from the spin axis sweeps around the sky like the beam of a lighthouse, so that an observer catches a flash once per turn. The model made a sharp prediction that a young pulsar should gradually slow as it radiates its energy away, and it was triumphantly confirmed by the pulsar at the heart of the Crab Nebula, the wreck of the supernova seen in the year 1054, which was found to be spinning down at exactly the rate needed to power the glowing nebula around it. Pulsars were the neutron stars that Baade and Zwicky had foretold. Hewish received the Nobel Prize for the discovery, controversially without Burnell, who has borne the omission with grace, and later gave away a $3 million prize to fund students from underrepresented groups. To understand the beam, one must picture the star's surroundings, which are not empty. A spinning magnet generates a powerful electric field, and Peter Goldreich and William Julian showed that this field is strong enough to tear charged particles right off the star's surface, filling its surroundings with a magnetosphere of plasma that rotates rigidly with the star. This co-rotation can hold only out to the light cylinder, the radius at which keeping pace with the spin would demand the speed of light. Inside it, magnetic field lines loop back and trap their plasma. The lines that cross the light cylinder are torn open and stream outward, emerging from small regions called the polar caps, and it is along these open field lines, above the magnetic poles, that the beam is generated. There, in the accelerating gaps just above the poles, the electric field flings particles to enormous energies. As they whip along the curved magnetic field lines, they radiate gamma rays, and in the ferocious field those gamma rays convert into pairs of electrons and positrons, which radiate more gamma rays, which make more pairs, an avalanche that floods the field lines with plasma. Out of this cascade comes the radio beam, and its defining feature is that it is coherent. The particles radiate in lockstep, in bunches, producing brightness temperatures of 1 trillion degrees and more, impossibly high for any ordinary process. Exactly how those bunches form and radiate is, remarkably, still not understood from first principles more than half a century after the discovery. The radio emission mechanism of pulsars remains an open problem, one of the enduring puzzles of the field. The true power of a pulsar, though, is that it is a clock, and the science flows from timing its ticks. Two numbers anchor everything: the spin period ranging from a few milliseconds to several seconds, and the rate at which that period lengthens as the star slows. From these one reads the star's energy budget. A spinning neutron star stores an immense reservoir of rotational energy, and the rate at which it bleeds that energy away as it spins down can be calculated directly. For the Crab pulsar, the figure is staggering, some 4 times 10 to the 38th ergs every second, and this, not any nuclear fire, is precisely the power that lights the entire Crab nebula. The young pulsar is the engine, and the glowing nebula around it is the exhaust. The same timing yields the star's age and its magnetic field. If the slowing is driven by the pulsar radiating as a spinning magnet, then the period and its rate of change together give a characteristic age, and for the Crab this formula returns about 1200 years, satisfyingly close to its true age of some 9.5 centuries. The same physics converts the timing into an estimate of the surface magnetic field, which for an ordinary pulsar comes out near 1 trillion gauss, trillions of times stronger than the Earth's. Because age and field depend only on the period and its rate of change, every pulsar can be plotted as a point on a diagram of period against spin-down rate, the pulsar's own version of the great classification diagram of ordinary stars. Young pulsars cluster in one corner and drift across it as they age, until they cross a death line beyond which the beam shuts off, and the star joins a vast, silent graveyard of neutron stars we can no longer see. Yet some pulsars defy that fate, spinning not once a second but hundreds of times a second, with a stability that rivals the finest atomic clocks. The first of these millisecond pulsars, found in 1982, completes a rotation every 1.5 milliseconds, whirling 642 times every second, a city-sized ball of nuclear matter spinning faster than a kitchen blender. Its spin-down is almost imperceptibly slow, implying a weak magnetic field and an enormous age. How can a neutron star be at once so ancient and so fast? An old star, by every expectation, should long since have slowed and died. The answer is recycling. A millisecond pulsar is an old, dead neutron star that has been spun back to life by feeding on a companion. In a binary, after the pulsar has slowed and gone dark, its companion star eventually swells in old age and spills its gas onto the neutron star. That infalling matter forms a disk, and carrying angular momentum with it, spins the star up, brighter and brighter in X-rays as it accretes, until it whirls hundreds of times a second. Accreting only 1/10 or so of a solar mass is enough to do it. When the feeding ends and the disk clears, a rejuvenated pulsar reappears, spinning furiously with a weak field and, because so little now breaks it, destined to keep ticking for billions of years. Astronomers have even caught systems flickering back and forth between the accreting X-ray phase and the radio pulsar phase, watching the recycling happen. The precision of these clocks has rewritten physics. A binary pulsar discovered in 1974, a pair of neutron stars in a tight orbit, was timed so exactly that its orbit was seen to shrink year by year, exactly as fast as Einstein's theory predicted for a system radiating energy as gravitational waves. This was the first evidence, decades before any wave was directly caught, that gravitational waves are real, and it won its discoverers the Nobel Prize. Today, astronomers time whole arrays of millisecond pulsars scattered across the sky, using them as a galaxy-sized detector, and in recent years, these pulsar timing arrays have found the first signs of a slow, rumbling background of gravitational waves washing through the Milky Way, most likely from the merging of supermassive black holes across the cosmos. Stranger still are the magnetars, neutron stars whose magnetic fields reach 100 trillion to 1,000 trillion gauss, the most intense magnetism known anywhere in nature. Robert Duncan and Christopher Thompson proposed that certain restless X-ray sources and repeating gamma-ray bursters were unified as a single kind of object, powered not by rotation or accretion, but by the decay of a monstrous magnetic field. That field is so strong it stresses the star's rigid crust to the breaking point and exceeds the threshold at which the vacuum itself turns strange under quantum theory. Now and then a magnetar unleashes a giant flare, a sudden release of more energy in a fraction of a second than the sun emits in tens of thousands of years. The Great Flare of December 2004, from a magnetar 50,000 light-years away, was so violent that it measurably disturbed the Earth's upper atmosphere, the light of a distant starquake reaching across the galaxy to touch our own sky. Even the smoothest pulsars occasionally hiccup, and these glitches open a window into the hidden interior. Now and then a pulsar's spin abruptly speeds up against the steady trend of slowing, and the cause lies in the superfluid within. Most of the star's neutrons form a frictionless quantum fluid that can spin only by threading itself with a lattice of tiny vortices, and those vortices snag on the crust. As the visible star slows, the pinned superfluid keeps spinning fast, storing up a lag, until all at once a swarm of vortices breaks free and dumps its angular momentum into the crust, jerking the star faster in an instant. And the newest window of all opened in 2017, when detectors caught the gravitational waves of two neutron stars spiraling together and merging, followed by a burst of gamma rays and glow, a kilonova, in which freshly forged gold and platinum were seen streaming into space. From the way the two stars deformed each other in their final orbits, physicists read off yet another measure of the neutron star radius, near 12 kilometers, in beautiful agreement with the X-ray results. The frontier is still expanding. In 2020, a magnetar in our own galaxy fired off a millisecond radio flash 1,000 times brighter than anything seen from the Crab, and it looked, but for its nearness, exactly like the mysterious fast radio bursts that flash from galaxies across the universe, tying at least some of those enigmatic signals to magnetars. And the deepest questions remain genuinely open: the true nature of matter in the inner core, whether ordinary or quark, the unsolved mechanism of the radio beam, the dynamics of the glitches, and the exact mass at which a neutron star must yield and become a black hole. New X-ray telescopes, a growing catalogue of mergers, and vast new radio arrays are narrowing the answers year by year. No laboratory on Earth can reproduce matter squeezed beyond nuclear density, and so, for the study of matter at its most extreme, the neutron star remains the only laboratory we have, a city-sized nucleus turning in the dark, still teaching us the deepest rules of the physical world.